Hi, good evening, everyone. Today we have almost the last linear programming application that we are going to review. So please go to Moodle and download MaxFlow, both the Word document and also the Excel file. So from next week, we start to work on Power BI. Also keep in mind, I think November 21st, I guess. So let me check. 22nd. So Efra will be here, and you have also assignment to present about the healthcare data. So just keep in mind, presentation date is November 22nd, and this is in the class. And it's good to present to him, so he's in the market. So in case later on you might looking for jobs in the healthcare industry, I think it's very good to get his feedback on your presentation. Okay, I'll give you a few minutes to download the file. So still this type of, as I said, operation still needs some creativity. It's not pure math. Even for you guys, you don't learn under the hood of the algorithm. So the under the hood of the algorithm needs some math, but being able to formulating your problem, it just needs some creativity. So, but again, as I already said, no worries. For your final exam, I don't expect you to suddenly get creative on your final exam. So if you see some question on your final exam, you already saw something very similar in your sessions. So we get to almost end of semester. I see some of you don't mute themselves. So let me see who's not muted. No, not all of you got muted. Okay, let's review the first question. The graph represents various flows that can occur through a sewage treatment plant, with the numbers on the arcs representing the maximum flow in tons of sewage per hour that can be accommodated. Formulate the linear program and a linear program model to determine maximum tons of sewage per hour that can be processed by this plant. So the sewage has an origin and a destination, and basically you see a network. You want to maximize flow from number 1 to number 7. Also, you see you have some arcs which represent your maximum amount that you can process. So basically, you maximize the overall flow, but it doesn't mean that you should maximize each arc. For example, arc 2 to 5 has capacity of 10. Also from 2 to 3, you have capacity of 7, but the input just 8. So input is from 1 to 2, but output from 2 could be divided in 10 and 7. So it just means that 2 arc won't be fully occupied. Give me 1 or 2 minutes to think about the problem. So you might remember in the high school science, or probably if you had engineering course in undergrad, so you had something about electricity. So if you have two parallel lines, the voltage in these two should be equal. Does it remember something like that? Maybe a long time ago. No? Okay. So no worries. So even your undergrad was if was not engineering, probably you should have something similar in your high school. But anyway, so look at the creative solution. Let's say we have a closed system. So everything goes from 1 to 7. We go from 7 to 1 if it's a closed system, right? We make an imaginary arc between 7 to 1. So if you maximize the flow from 1 to 7, it just means, since it's a closed system, you have to maximize the flow from 7 to 1. Otherwise, the system won't work. So what we did here, we actually introduced an imaginary arc or new arc and just play with the problem. So we're just saying that let's add that arc, maximize it from 1 to 7, which goes through several arcs. It's just equivalent of maximizing from 7 to 1. So now you did it with just one arc instead of how many? 1, 2, 3, 3 here, 3 here, 10, 12. So instead of taking care of 12 arcs at the same time, just take care of one arc from 7 to 1. So some of you, I think, understood. Some of you, it seems to have big questions. So you guys want me to explain again? Yes. So we want to maximize the flow from 1 to 7. It's a very difficult problem to formulate because you have several arcs and points that comes in and out. We just introduce a new arc from 7 to 1. We're just saying that whole of the upper branch is equivalent to lower branch. With the flows that goes 1 to 7, eventually would go from 7 to 1. These two are equivalent, so maximizing the upper branch is equal to maximizing the lower branch. But they have to be equal. We forced it to be equal, actually. So now the problem is much easier. You maximize the flow from 7 to 1, and the remaining are similar to other transportation problems. So you might remember 4.4 in should be equal out. Whatever comes in should go out. It's like warehouse in the transportation problem. Also, you have other constraints. So for each arc, you have one constraint. Let's look at, okay, I'll give you 1 or 2 minutes if you want to put some comments on your file or notes. Then I go to the solution. All right, so I think the setup is familiar with you. It looks like a transportation problem. So on the rows, you have the arc addresses from where to where. And also on the column, you have your nodes. So for example, for point 1, you have 3 outputs and 1 input. The input comes from 7 to 1. So it's the reason coefficient of 7 to 1 is 1, but 1 to 2, 1 to 3, 1 to 4 are negative. Let's look at point 2. So for point 2, from 1 to 1, 1 to 2, you have input. From 2 to 3, 2 to 5, you have output. So the coefficients are negative. So the overall setup is exactly the same. Now, the differences is on the objective function and also your constraints. So the blue cells are decision variables, right? So it's similar to before, except for the last one, because 7 to 1, maybe I can change it to green, so for less confusion. So the green 7 to 1 is your new objective function, because we want to maximize the flow from 7 to 1, because it's exactly equal to flow to 1 to 7. So next to the decision variable, I put the maximum flow, and I know my decision variable in the blue cell should be less than the constraint. So you might ask me why I put 999 for the last one, the maximum capacity from 7 to 1. This is just an arbitrarily large number. Doesn't have that much of meaning. I put the maximum capacity of this one 991 or maybe 2000, 10 million, doesn't matter. I just want to basically say this link doesn't have any limitation. This is just a made up link. I don't want to oppose new constraints by a new imaginary link that or arc that I create. So 999 there just means a big number. But for computations, I cannot type big number. I just should put a number. If I just type big number, computer cannot just do calculations. I just should put a number that looks big to me. So 999 looks big to me. So yellow cells in the bottom, these are just basically decision variable times the coefficient of link. So it's in either it comes in or out. The summation should be equal to 0 because for each node, whatever switch comes into the node should go out. So those yellow cells is just summation of all +1, -1s in and out switch. I want them to be equal to 0 because I don't want to store any switch on each node. Okay, so let's look at the -1 means just it just means whatever these are the links that showing the output flow. It just means, for example, 1 to 2, 1 to 3, 1 to 4. All of them just switch going out of 1. But for 7 to 1, you have internal switch. So switch coming to 1. So +1 is that. It just means coming to a node. Getting in, +1. Going out, -1. Let's go to the solver. So if you look at objective function, is D17. I just want to maximize the flow from 7 to 1. Is a maximization problem because I want to maximize the flow. My decision variable is D1 to D17. These are the amount of flow So the amount of flow among decision variables. I have two constraints. The first constraint, D5 to D17, should be less than C5 to C17. I'm just saying that the flow should be less than capacity, because each link has a certain capacity. The last constraint, G18 to M18 equals G19 to M19. It just means whatever switch comes in should go out. I don't store any switch. Yeah. And also I said on constant variables to be non-negative. It doesn't mean to have any negative switch. So if I click on solve, okay. Okay, so as you see, this is the flow. The maximum flow is 24, which happened from 7 to 1. So at the same time means the maximum flow from 1 to 7 is 24. Also, look at the yellow cells. Yellow cells, it just means those coefficients times two decision variables, and summation of all of them are 0, means whatever switch comes in goes out. For example, let's look at point 2. So 8 times 1, 8 comes in. 0 times 7, 0, so it doesn't affect it. Negative 1 times 8, 8. So I have 8 plus 8 in, minus 8 out. So 8 minus 8 is 0. So all the switch that get to the point 2, they went out. So as you see, summation of all the decision variables on the yellow cells are 0. It just means, which should be, I don't store the switch. So this is the way that I solve the problem. So it's super creative. I am pretty sure the first one who solved the problem will spend like hours. It's because it needs some creativity. It's not mathematical problems. Okay, I'll give you a few minutes if you want to add your comments. So I'm pretty sure it might be a little challenging because it's usually you don't solve mathematical problem this way. Yeah.
What if it's a dynamic moment? One, you can export to node 2, and then node 2 can start transport the switch to more other nodes.
Could you say your question again, please? You said, what if you have a dynamic problem?
Like the beginning series was sent from 1 to 3 and 4. And then 2 can start, 2 and 3 and 4 start to transporting the sewage. But at the same time, other sewage are still exporting from 1 up from 2 and 3 and 4.
Oh, okay. So you said switch comes to 2, 3, 4 at the same, then we stop and again send from 1, 2, 3, 4 at the same time?
Not a stop. Like it takes time from 1 to 2 and 3 and 4. The ones when 3 and 4 accept the switch and start to install. At the same time, with the first off, is sending the switch.
Actually, that's a really good question. If you want to solve those problems, you need to know dynamic programming. That's I think I'm pretty sure there's a course for industrial engineering, they call it stochastic operation research, or also they have a dynamic programming. So you need to take those courses. It's way above the content of this class. Yeah, but yeah, we have something. Even you can introduce some probability. So what if, like for example, link 3 to 7, in like 20% of time, maybe it gets clogged. So and you need to use other links. Or maybe sometimes link 4 to 6 with a certain probability it doesn't work. So what happens? So these are all under stochastic and dynamic programming. And if you're interested, I'm recommending to take either PhD of operation management or industrial engineering, but for learning them, you don't have to. If you want to go further, higher education, these are the paths that you need to go through. But these are just 2 books. Maybe you can study those books. And I mean, these are like, could get way more complicated there. So people maybe study 4 years on these topics. All right, good question. Yeah, unfortunately, I cannot answer your question tonight. But I had those courses long time ago. Even I'm not sure if I remember how to solve it, but I have learned through those courses. Yeah, stochastic operation research and dynamic programming. Even some computer scientists, they study dynamic programming too. Yeah. So dynamic programming means for each step, you have several options. And maybe even sometimes, oh my God, in the very simplistic way is what your friend said. So each step, you might have several options and you might just go in different ways. So, and what is way more complicated than, so let's just stop at this point. Let me go to Amazon if I can find the book. Dynamic programming. I got it. So for computer scientists, they study algorithms. So they have an algorithm course or dynamic programming optimal control. These are, I think, the books that explain very well. Yeah, computer scientists and somehow industrial engineers, they study this concept. Okay, second question. Simple transportation problems exactly look like what you have seen. But look at the demand and supply. So first of all, our supply is more than demand. So it seems that we can't provide our demand. But look at the basically each link capacity. So UB stands for upper bound, means upper bound constraint. So in order to fulfill demands on point 4, at most you can send 35 units from point 1 and 35 from point 2. 35 plus 35 is 70, right? So it's less than 80. Means although you have enough production capacity, but you cannot fulfill the demand because you have some constraint on your link. Same as for point 3, the upper bound from 1 to 3 is 40, 2 to 3 is 30. So the maximum delivery is 70, but your demand is 75. So in these cases, we say we don't have any feasible solution. Definitely, you cannot fulfill your demand. So let's just solve it. So this is a very basic transportation problem. I think we had like 2 or 3 before. So I already just put the cost, capacity, and the blue are decision variables, and yellows take care of for constraints. If I go to the solver, so I'm trying to maximize G15. G15 is just basically decision variable times cost. Is a minimization problem. Usually in transportation, we minimize the transportation cost. Decision variables is F7 to F10, these blue cells. And I have 2 types of constraint. First, F7 to F10, less than H7 to H10. These are just upper constraint. Or sorry, upper bound constraint. I cannot send more than what can I deliver. Second constraint is talking about demand and supply. J11 to M11 more than J12 to M12. It's just saying that those yellow cells for supply, which is the negative sign, if I say more than that, it means like minus 19, minus 80. But for demand part, which is 75 and 80, I want at least provide the demand. So we know that we cannot solve it because it's not feasible to provide the demand. Let's see if Excel can understand. Yeah, we have a feasibility error, so it's not feasible. Which we already knew that because we know that because of those upper bound constraints, we never can provide those demands. If you look at the problem, I didn't say provide the demand or solve it. I just said try to meet the demand. So if you remember in the previous problems, like here, you maximize the flow. Here, when somehow there's some similarity between these problems. I'm saying try to fulfill the demand or meet the demand. It just means maximize whatever you can send. If you maximize whatever you can send, you do your good. What can you do? You can do the best thing that you do. We try to meet the demand. It just means we try to send as maximum as possible that we can. But maybe we cannot fulfill the demand. We just do our best. So 2 things we can do. So first, in here, maybe we change the constraint. Instead of saying the yellow cell is greater or equal than next line, the basically supply demand, we might say less or equal, or maybe equal at most. But what else we can do, again, is pure creativity. I never expected anyone can solve it first time. So as you see here, I added 2 links and a dummy point. So this dummy point has unlimited demand. Upper limit is 100. Again, 100 here just means a large number. So it could be 2,000, 3,000. I just, instead of writing a unlimited link, I just say link with a very high upper bound. And also it's very expensive. Look, so $999. So much more expensive than other links. So what happens in this case? So you send everything from 1 and 2, but it just tried to push everything to the right side, to the black link, because the red links are very expensive. So by creating two imaginary links at one dummy point, we force our model to send everything to the black side or black links because the red links are very expensive. Just wait 1 or 2 minutes if you have questions or you want to write some notes. So let's look at the solving section. Still, we try to minimize multiplication of blue or decision variable times the cost. I somewhat changed the constraints, but first of all, F7 to F12, we still have decision variable should be less than the capacity. Also, J13 to N13 should be less than equal these next line. Because it cannot be greater or equal. So if you press solve, now we have a solution. So the cost is not 6,000, it's just the overall cost, because I already introduced two expensive links. So the actual cost is just the first blue links times its cost. So still, I'm not sure if you still have a question about why I'm saying J13 to N13 less than J14 to N14. So I'm just saying that, first of all, I know that for number 3 and number 4, these are my demand form. I cannot provide more or equal. Also, I'm pretty sure at the end, the first two yellow cells for 1 and 2 won't be more than 100. Or are not less or equal, or won't be less than minus 100. Why? Because if these two, let's say if they were 110 or 120, whatever, it just means I have some extra production. So I don't have any capacity to send to the black ones. They should go to the dummy points, which are very expensive. So I'm pretty sure for number 1 and 2, it hits 100, and it won't be more than that. It doesn't make sense if they do 120, 130, because the maximum capacity 100. But I'm pretty sure they won't go more than that, because if they go more than that, it just means there are some extra products that they should send to the dummy parts, which even makes my objective function more expensive. So because the overall logic is minimizing this problem, the cost, minimizing here just means you produce 100 here. You cannot produce more than that. I give you a few minutes to think, and if in case you have questions, you can ask me, but I think it's good if you think about the overall logic. And it's good to ask questions because at the final exam, I give you something similar to you guys. So since this is a hybrid class, I cannot give any other types of question, because if I ask you some writing question, it would be from textbook, and some of you even are not in this country, so I don't think that is fair. Also, for other parts, it's couldn't possible. The only part that I can ask you in the hybrid mode is this type of questions. And I give you a couple of days to just solve the problems, and the final exam is the individual assignment. You shouldn't share your solution. Okay, let's look at the question number 3. Try to satisfy the demand with the minimum cost. So instead of network, you have a table. So it seems to have 5 points, L1 to L5. So you have the cost and capacity of each link. So from L1 to L2, the cost is 12 and the capacity at most 8, and you have the same for the others. Draw a network diagram. Flow of cars is given. So 15 cars are supplied from L1 and L5. So I think it should be okay, no, sorry. 15 cars supplied from L1 and 15 cars from L2. At L5, 10 cars are required. At L4, 20 cars are required. Here's a network flow with the lowest cost, unit cost, and capacity of each road is given. Make sure the model converges. So we know our supply points and also demand points too. So L1 and L2 supplies, L5 and L4 has some demands. I give you 1 or 2 minutes to think about the problem. So it seems when I talk about convergence, it seems the problem is not feasible. And I made it obvious. But if you look at the figure, so we have 30 supply, 30 demand. As you see, it just means you should send out everything that you create. So from L1, it seems it's possible to send out 15 units because L1 to L3 has capacity of 6, L1 to 4, 8, L1 to L2, 8. So the summation is more than 15. But for point 2, L2, at most you can send out 14 units because capacity from L2 or constraint from L2 to L5 is 8, L2, L3, 6, summation 14. 14 is less than 15. So for sure, you cannot provide your demand because it's not possible to send out all of products that you produced. Sometimes it's very hard to understand the problem, but I think here it's kind of obvious. But usually when I give you a network and you have one side you have supply, one side you have demand, and if you cannot provide the demand, it just means you have some extra supply that you should just send them to a dummy point. When you send extra to a dummy point, the remaining pushback to the black side, or it would maximize the flow. We want to maximize all the cars or all the flows that we can send from supply point to the demand points. Let's just solve it. I press solver. So first, we want to maximize multiplication of decision variable times cost. So I minimize it by changing E7 to E14. Our first constraint, E7 to E14, less than G7 to G14. These are my capacity constraint. Also, H15 to L15, less than H16 to L16. It takes care of the supply and demand. You should send less than supply, and at least you should provide the demand. We got the feasibility problem. It just means, so when in the maximum flow problem, you see feasibility issue, it just means you have some extra supply you cannot send you couldn't fulfill your demand. So as we already discussed, what can we do? We added dummy points. That dummy and try to maximize the flow on the black links. How it gets maximized? We know that the extra supply, if they should go to the actual network, because if you have some extra, they go to the dummy point that is very expensive. So your model logics push everything to the actual network or maximize the flow, because if it doesn't maximize, it has something to send to a dummy point that is very expensive. So since your function is minimization, the only way that it can minimize is through maximizing your flow and sending as less as possible to the dummy points. Okay, so similar to previous problems, I added two dummy links, L1 and L2 to dummy, with a very large capacity and very expensive cost. So in 999, it's just arbitrary large numbers. We also changed the constraint. If let me show it to you. So now I'm just saying H17 to M17 less or equal H18 to M18. It was opposite. It was more than that. Now it's less than that. So for H17 to M17 be less than H18 to M18, fresh to yellow cells are just saying that they are either 15, minus 15, or minus 16, 17, 18. But I know since I have a minimization problem, it would stay at 15. It won't go more than that because it's against minimization logic. So let's solve it. This is the answer. Again, the actual cost is just decision variable times the cost. Because these two links are just imaginary arbitrary links. So you stay, the actual cost is just actual decision variable times the cost. Okay, give me a few minutes if you want to put some comments or might have some questions. Yes. So you saw that the problem was not feasible. It just means you have some extra supply that cannot, or basically you cannot fulfill your demand. So it's not feasible to fulfill the demand because your links are limited. So what we want to do, we want to maximize the flow of the car or supply from supply point here, L1 and L2 to demand points. So the overall logic is minimizing the cost. So the mathematics behind of this Excel, or in general, we call them operation management or linear programming. So this is those mathematics, your problem must minimize. Okay. So how we minimize? So we made a very expensive dummy points with unlimited capacity. And we just said that we should at least produce 15 products on each supply point. So we create 15 and more than that. but we know that we cannot deliver 15 because there's some limitation. So what happens, since we already said, please produce 15 or more than that, first, since the logic is minimization, first it tries to send everything to those cheap links. So it maximizes those links because they are much cheaper. Yash, you didn't mute your speaker. So the logic, the math logic behind that is minimization. So how it does, it sends as much as it can to the cheap links. The remaining have to go to the expensive part. So the role of expensive part is just saying, since the problem is minimization, we have the role of the max dummy expensive point is gets as minimum as possible. The logic is minimization. It just means you should send everything to the cheap part as much as you can, and the surplus have to go to the dummy points. So the role of dummy points for just pushing as much as you can to the cheap part. So without the dummy, so if you have a feasible solution, you don't have to have dummy. But just look in this problem. First, we didn't have any dummy points. It was not feasible, right? Because you cannot provide 10 and 20 there. Now we provide 10 at point 5. For L4, just provide 2. And the extra 2 goes to the dummy points. Dummy point, yeah.
Professor?
Yes?
So we're still sending only 14 for each of the L1 and L2. We're not sending 15s, right?
So,
two like 14.
so check what we did. So for L1 to...
I think L1 to L3.
So L1 to L3 and 4, you sent 14.
And then
L2 to 3 and 4, yeah, 14. You send 14 from each.
So you're only sending 14 from each. So like those
Yes.
two just go to the dummy variable. So we don't count them. It's just like we're finding the best solution, as you said, right?
Exactly. We don't count those dummy because these two, the cost is 2 times 999. This is just arbitrary coefficient that we put there to force everything to go to the cheaper part. Okay. So the actual, yes, you are right. The actual cost is just the actual decision variable times the cost of the link.
Okay, thank you.
You're welcome. Okay, let's look at the last maximum flow problem. Okay, the graph represents various flows that can occur through a sewage treatment plant with the numbers of arcs represent the maximum flow in tons of sewage per hour that can be accommodated. Formulate LP just means linear programming. It just means mathematics behind of this problem. Formulate an LP model to determine the maximum tons of sewage per hour that can be processed by this plant. There is a constant cost for maintaining each pipe given in the table. Maximum dollar available are 25,000. So you have if you use each link, you should have a constant cost So what does it mean? It means maybe you shouldn't use all of the links because there is a cost associated. So we should take care of two things. First of all, should we use a link or not? If you use a link, maybe you need to you make some pipe which are costly. So now we have more complexity here. First of all, we should take care of two decision variables. One decision variable is if you want to use a link or not, and how much you should use those links or not. So the cost of usage per ton is over link. So for example, if you send 2 tons from 2 to 5, you should pay 10 times 2. Also, if you want to use 2 to 5, you should pay $6,000. So we add more complexity here. So first of all, we have two decision variables. One, should we use a link or not? If we use, how much should we send through that? I give you like 1 or 2 minutes to think about it. So as you see in this transportation, it looks like a transportation table. So I have two sets of decision variable. First, how much should I send to each link? The first blue cells. The second blue cells are on the right side. Should I use a link or not? If I use it, 1, otherwise 0. So now let's talk about the yellow cells. So first of all, if I end up saying all 6 or first blue cell on the right is 1, it just means I use that link. Now I should just take care of left side, which is decision variable should be less than maximum capacity. So if my right decision variable is 1, I should just need to take care of left decision variable to be less than capacity. If you it just means if you want to use a link, the amount that you send should be less than capacity. Also, if the right side is 0, it just means your left decision variable should be 0 too. Because if you don't use it, or decision variable 0, doesn't mean that you should take care of basically capacity of the link. If I go to the problem again, also we don't record or we don't keep any switch, so everything comes in should go out. So it's the reason I put here 0. These yellow cells, it's just multiplication of those link coefficient, either plus or minus, comes in or out, times decision variable on the left side. It just means summation of the flow in and out should cancel each other. And finally, the cost is just has 2 sections. So, but I think, let's say, yeah, I think I should fix it, but no, that's okay. So the cost is just a decision variable of using or not using times the cost of building the link. So you use some links, or the coefficient is 1 times its cost, and basically you must use some product of the cost column times associated decision variable of if you use it or not use. So let's look at the solver. Hopefully it makes more sense. So first of all, D18, which is multiplication of cost to its decision variable. We try to, I think I had several typos here. So, but let's see. D18. No, that's okay. So maximizing the flow, but D18. Yeah, I forgot here to say that. I think I didn't put the figure. Yeah, I forgot. But we already know for maximizing the flow, we create a link from 7 to 1. Maximize it from 1 to 7 is equals 7 to 1. Since I already put it there, I didn't put the extra link from 7 to 1. Okay, I will update your Moodle later. I put a link from 7 to 1. Since I already did for the previous one, I expect that I was thinking it's not needed, but basically for maximizing the flow, instead of taking care of the complex network, we just connect the last point to the first one and try to maximize that red link. Sorry, I didn't put it here, so it might be a little more confusing. Okay, maximizing flow from 7 to 1. D6 to D18, less than C6 to C18. So the flow should be less than maximum flow. D6 to D18, less than P6 to P18. Basically, we just say that if you already take care of the maximum flow there, here you don't need to take care of maximum flow again. You just take care of 0 once. So I put an arbitrary large number here. And the only reason for that, I wanted to associate flow to use or not. These values are more than 1, 8, 9, 8, 17. So instead of, to make my life easier for connecting these, because these two should be associated, these two blue columns. If you use it, you should take care of their flow. So it means there's some connection between two. So instead of connecting these two blue columns, I made a very large column. I put the arbitrary value of 99. Instead of saying that if it's 1, it should be 8, it's equivalent of saying that 8 should be less than 99. Might be a little confusing. I think it's a little over the content for the class. So I don't give it to you in the final exam, no worries. I think it's very hard because it has several creativity works, so it might be a little challenging. So I think it's a little out of content for the class, but let me just explain, but I don't expect you because it has several complexity. So first complexity was flow and the maximum flow. The second, if you have the link or not having the link. Instead of saying, so do you accept that these two are kind of relevant, the yellow column and the blue column? It's just the blue column times a very large number of 99 is a yellow column. So if it's 0, this should be 0 2, but 2.2 times 10 raised to power of minus 15. This is actually 0, but it didn't round it up. So let me write an actual number. So cell D18 is actually 2.2 times 10 raised to power of minus 15. Do you believe that it's almost 0, right? It just excels some basically rounding issue, but this is 0, or literally 0. So 0 is less or equal than 0. So it passed. What about this 99? 99 is more than 8. So whenever I have 1 over there, I have 99. So I have something more than 0 here. But whenever the right blue cell, I have 0, the yellow cell is 0. Here I have a 0. I think the next constraint makes more sense. G19 to M19 should be G20 to M20. It just means everything comes in, should go out. We don't store it. N22, which is the cost, should be less than 25 because we said at most we have $25,000. So we put that constraint saying that total cost should be less than 25. And last, 06 to 018 should be binary. The right blue cell should be either 0 or 1. So binary means there should be 0 or 1. So is this yellow column still confusing? If it's still confusing, no worries. I mean, I accept that there's multiple complexity here. I just want to introduce a condition. Whenever here is 0, that should be 0. Whenever it's 1, I don't care what is there because whatever I have here, for sure is less than 99. The only constraint, they check with the maximum capacity. Again, no worries. I know this is really, I never give it neither as an assignment or final exam, but just keep in mind, in some problems, you might have multiple conditions. You have multiple decision variables that interact with each other. So when you have multiple decision variables that interact with each other, you should take care of some connection or association of them. Here I tried to find association of between either I built or not with the capacity. But I know it's a little out of the content, but maybe just for something extra, just keep in mind, you might have several decision variables that are in different dimensions and could interact with each other. Questions? I see, when I don't see, with mask, I cannot understand how you think, but it seems some you have several questions. Okay, people over Zoom, do you guys have questions? Except for the last one, which might be a little out of content. So if you guys have questions, you also can raise your hand or use your mic.
Just one question. So
sure.
Just as we did for, like, you know, all of the 3 first problems. So every time, like, we don't meet, you know, the requirements, or like when the solver does not, you know, allow us to like solve the problem, then we just create a dummy variable. I mean, the thing right there. So when we send like
actually, you ask a very tricky question. Sometimes, do you remember, I think first time you found one of your friends found a typo in my problem, so maybe you formulate in the wrong way, so you Excel cannot solve it. So if Excel cannot solve it, maybe either you made a mistake, or like a maximum flow problem, you need to add a dummy variable. So you should first check if you made any mistake or not.
Yeah, that's very difficult to like.
Yeah, that could be difficult.
Find like the mistake.
Yeah, but no worries. I don't give you the last question. I think it could be. It's like several complexity intertwined together, but I think for other problems, I think it's pretty easy. If you just solve 1 or 2, and I give you some assignments, it should be very easy for the final. And I give you some sample previous year final exam, so you can already see how was their exam. So yeah, I'm pretty sure you would be in the really good shape for the final.
When is the final exam?
Last week I give you a couple of days. It's like an assignment. So your final exam is like an assignment that you have like a couple of days to submit it.
So it's a take-home exam, right?
Yes.
Okay. Because I won't be there like last week, so I can do it like on my.
Yeah, you can. Yeah, you don't have to come. I mean, you won't be in the class, so you take the exam at home. It's like a Moodle, so you go to it's like a Moodle assignment. You take it and you submit your codes, or if you write on a piece of paper, you should submit everything.
Okay.
If it's a piece of paper, you should take a picture and submit the picture. Okay, by the way, I just forgot to say, so next, I think some of you were in my morning class, so next summer, most likely we have an experimental class in blockchain cryptocurrency. So the first part, you learn about the concept and you learn how to do trading. And the second part is very technical, so you need to know good knowledge of Python. So you make your own blockchain and your coin. Maybe you can sell it too if you want. Huh? That means we offer first time to see the feedbacks. And we might, it's because it's a summer course. Yeah, it's a course. So if you graduated by summer, you can register as free. But if you're a student, you can take it as one of your, I think, I'm not sure for every major, but I think for most of major, they say it could be an elective course. So if you're graduated, it's free. If you're still a student, you can take as an elective course. So you don't pay more, so probably you substitute with one of your courses. But I'm not sure how complicated, how technical we would go. So some already has my advanced programming class. Arjun has it, right? So let's assume like 2 or 3 times more technical than that. Because we don't want you guys to train as a trader. We want you guys to know the technology behind of that. So, and also it's good for trading. So there is some kind of meme coins come to the market. People just buy as a gambling, but there's nothing behind of that. So usually people lose a lot of money. But I think if they know the technology behind of them, they can have a better understanding, is it worth of investment or not? Or even you think some coins are not worth in terms of investment, maybe you do, if you want to do gambling, at least you know that you're doing gambling. And I'm against gambling, but at least if you want to do gambling, you should know that you are doing gambling. Okay, any questions? I don't see any question, but I guess when I see your eyes, I think the last question was like too difficult, right? Which is right. I think even when I was a student, it was difficult for me too, because it's like has several complexity intertwined to each other. Okay, that's for tonight. Thank you very much. Take care. From next week, two things just keep in mind. Next week we start Power BI as some challenges. So each class I give you some challenge and we try to solve those challenges to learn. If you don't have PC laptop, that's okay. You don't lose any credit. But I wish you could learn some Power BI. I guess it's good for job market. So it's optional classes, but I certainly recommend to take that. So why not use so you learn extra visualization software. And just keep in mind, November 22nd, Efrat comes and you present your effort to him. And I think it's very good. He provides some feedback on your presentations. Take care. Thank you very much. I think, let's say there's 2 questions, I guess. No, there's 2 thank yous. Okay, take care. Bye.